Hello, welcome to second week of computational quantum chemistry, and this week we'll start with the discussion of Hartree-Fock molecular orbital theory. Hartree-Fock molecular orbital theory is the crux of computational quantum chemistry. Almost all the electron correlation methods or the subsequent theories we are going to discuss, they are going to based on Hartree-Fock molecular orbital theory. So it's important to understand its theory properly. At the same time, Hartree-Fock molecular orbital theory is something which we know from our chemistry courses. So this gives you chemical intuition into the various chemical reactions happening and help us to interpret our numbers. So this is the molecular Schrodinger equation. This is how it looks like. And if you go at the shape of the Hamiltonian, this is how the Hamiltonian look like. So the first term is the electron kinetic energy, the second term is electron nuclear attraction, the third term is the electron repulsion, and because we are working in the Born-Oppenheimer approximation, the nuclear repulsion term is added to the electronic Schrodinger equation, and this is a constant term. Now if you see all these terms, the first and the second terms are actually depends upon the coordinate of one electron only. So these two terms are often clubbed together and generally called a core Hamiltonian, and this is the Rij term. Because of this Hamiltonian cannot be exactly solved, and this form of the Hamiltonian cannot be solved exactly. So one need to take some kind of an approximation, and before taking any approximation, just remember there are three kinds of approximations possible. One is variational, second is perturbational, and third is via projection techniques. We are going to see all of this when we are going to derive the electron correlation method. But for Hartree-Fock molecular orbital theory, we are just going to use the theory of variation. But before going into that, let us brush up how an wave function actually should look like and what are the properties. And one of the important properties which we have not discussed up to now is spin, and we know that the Sz operator, when it acts on the spin coordinates, it gives you the, it's an eigenvalue equation, it gives you the ms value. If ms value is half h cross, the spin is called alpha, and ms value is minus half h cross, it is called beta. I will reiterate this again and again, that spin does not mean rotation like this or this, up or down, they are just representations. Spin is a quantum mechanical phenomena, so we exactly do not know how it looks like. Now of course, if we consider the spin, we get what is called a spin orbital chi, and the spin orbitals how they look like is you can have a spatial part, that is a psi 1, small psi 1, and an alpha part. If I multiply them together, so the spatial part and spin part, if I multiply them together, I will get a spin orbital. Similarly, I can have a chi 2 where the spatial part is same and the spin part is different. Remember, the spatial part does not need to be always same, and when we will go to unrestricted treatment, we will see that the spatial part can also be different for two orbitals. And now because of the spin, there is the property, because I am dealing with electrons, they are fermions, so I have to ensure that they actually observe the principle of antisymmetry, so that if I change the coordinate of electron 1 and electron 2, the wave function should change the sign. One of the easiest way to achieve is to use the so called Slater determinant. Now why the Slater determinants are so important, or why they are so essential for discussing of any wave function based quantum chemistry method. If you see the form of this Slater determinant, my spatial orbitals index are on the column, whereas my electron index are on the row. Now if I interchange any of it, the rows or the column, the wave function will essentially give me a negative sign. That is a property of the determinant. Secondly, if I put same electron in the two of the orbitals or two different electron in the same orbitals, this will, because the rows and columns will be same, so it will be 0. So essentially the use of the form determinant helps me to correctly give the antisymmetry properties. So for all the subsequent discussion, we are going to use Slater determinant only, and this Slater determinant is named after the name of John C. Slater, who has developed this in 1929. Now we are going to discuss Slater determinant for any general system. Let us say for an n electron system, this is how it will look like. We will see the same form. The spin orbital index are actually given in the column and the electrons are in the row. Remember, Slater determinant can only be written in terms of a spin orbital, it cannot be written in terms of a spatial orbital, and this is a general n electron system. You can always generalize it for a 2 electron case. Now What is written is a shorthand notation. In the shorthand notation, you just write the diagonal element because you don't want to write the entire determinant all the times and the corresponding index. So, what you write is the diagonal values of these determinants, and this is essentially mean the same thing. This is just a shorthand notation of writing it. So, in the Hartree-Fock approximation, we want to determine the best single determinant which will give the lowest energy in the single determinant picture. So, Hartree-Fock approximation starts with the assumption that my wave function is just consist of a one determinant. Of course, it is an approximation. The exact wave function cannot be a single determinant, and it can be proved that it cannot be a single determinant. So, I am working with a single determinant picture. Now, I want to get that single determinant which will give me the lowest energy in that single determinant picture. So, Hartree-Fock determinant gives you always the best determinant in terms of energy because it will lead to the lowest energy possible in the single determinant picture. If you generate any other determinant, it will have either same or higher energy than the Hartree-Fock, and that comes due to the fact that Hartree-Fock is solved using variational principle. Now, I can take any Slater determinant in principle, and I am saying that if I do the Hartree-Fock, I will get the best possible single determinant. Then the question is that, let us say if I take an arbitrary Slater determinant, how I can improve on that Slater determinant? Let us try to first understand it physically. This is an helium atom, and of course, I can use the optimized one electron wave function. For example, I can just use the hydrogen atom for the beginning. So, I can define the spin orbital as the hydrogen 1s spatial orbital into alpha spin, and the chi2 as a hydrogen spatial orbital 1s into beta spin. And we know this is the shape of the hydrogen of 1s orbitals. We have the exponential part which is a Slater function. Now, remember, if you want to use the hydrogen atomic orbital for helium, that may not be a good approximation because there is an electron-electron repulsion which was not there in the hydrogen atom. It has only single electron. So, how I can improve upon hydrogen atom orbitals? One of the approach is to use the concept of screening. That electron, because it has two electrons, so these two electrons will actually skin the positively charged nucleus. So, here this blue part is the electron and the red part is the nuclei, and what we assume that each of these electron will screen the other electron from this effective nuclear charge. So, that means the charge what is faced by each of the electron is actually not 2, but slightly smaller than 2, and that is why we have to replace this equation in place of the Z in the hydrogen atomic orbital. I can get a new set of optimized set of orbitals where I have the Z as Z effective which is slightly less than 2. So, that means in my orbitals there are a parameter which I can change to actually include the physical effect. So, that means I can get a better orbital by actually changing the parameter Z in this case, and where Z is where the Z effective is Z minus a sigma which is called a chemical shielding parameter. But this is an ad hoc treatment. I do not have a generalized way of getting a better orbital unless I want to. What happens when we go to molecule? How I will take care of the shielding? So, this is not a very compact mathematical picture, and why I want to go to a compact mathematical picture? Because the mathematical picture can be solved easily using a computer. That is why I want to develop every chemical phenomena I have in terms of mathematical treatment. Now, how I can get it generally? By using the formula of variation. So, this is my energy functional psi star h psi d tau, and this is the normalization. Using if I use a just single Slater determinant, so I take the form of the capital psi as a single Slater determinant, if I do the mathematics, what I will lead to this formula of the energy, where the first term is a 1 electron term and the second term is a 2 electron term. We will get to the form of this energy, but if you do the mathematics, this is the form of the energy I will get. Now, this is a core Hamiltonian, the first part where I have the 1 electron operator. Basically, it is an electron kinetic energy and the nuclear electron attraction, and I expand them in this terms of basis where psi I are the small psi I are the spin orbital. Of course, here I am going to use a treatment. I will do all the derivation where the number of alpha electron is same as the number of beta electron. So, I can integrate out the spin and actually can work in terms of spatial orbital. So, the expression which is given here is a spatial orbital. Next term, the J. This is called a Coulomb integral. And this is something, it has something interesting physical interpretation. So, now if I see the form of this one, on the left hand side I have psi I 1 star and psi I. On the right hand side I have psi j 2 star psi j 2 and then there is an 1 by R12 term in between. Remember, this 1 by R12 term is a multiplicative operator, so I can shift the psi j and psi I between left and right absolutely without any trouble. Now, if I try to visualize it, what it actually means like. So, if I write this part and bring my d tau or dV here, then this is like a electron density. Remember, the probability density is psi I star psi I d tau. So, this is like an electron density of electron 1. This is the psi j star 2 psi j dV 2 actually density of electron 2. So, there is a small volume element dV 1 and dV 2, they all correspond to electron density and they are interacting with the R12 term. So, this is the potential energy term and this looks like a classical Coulomb interaction. So, this is actually called, that is why this is called a Coulomb integral. Now, what is K? The term which is given in red. If you see the K, how the it is different from J. So, what I am doing now, in place of psi I, in the case of J, my both the terms in the left was contains coordinate of electron 1. What is we are doing here in the case of exchange, the K, I am replacing the one of the terms here by electron 2. So, my left hand side electron 1 and 2, the right hand side also has electron 1 and 2. And this is confusing. How can I define density where one electron coordinate is 1 and the other electron coordinate is 2? And actually we cannot, because exchange integral has no classical analog. This arises due to the antisymmetry of the wave function. So, exchange is essentially a quantum mechanical phenomena, this which does not have any classical analog. Now, to see the form of the energy again, if you see the term HII and the J comes with a positive sign and minus K comes with a negative sign. So, actually in the case of bonding, it is a exchange term which actually reduces the energy of the system, making it stable. So, exchange is something which is responsible for stability in quantum chemistry. So, now I have the form of the energy, I will variationally optimize it and then I will get to the best possible single determinant. So, that how to do this variational optimization, I come to the picture of Hartree-Fock theory. So, in the Hartree-Fock theory, if I do a variational minimization of the energy functional, what I lead is to what is called a Fock equation. F psi I is equal to epsilon I psi I, where epsilon i's are my orbital energies. And this F is called a Fock operator, which has the following form, which is H core, which is a 1 electron operator, and then I have the J and K integrals, which are effective 1 electron operator. If we see the form of the J and K, is actually has a summation over the coordinate of electron 2 and it is integrating over the dV2. So, I am actually integrating out the coordinate of the electron 2. So, that means these are effective 1 electron operator. Now, two things to note here. First of all, what I am physically doing, I cannot solve the eigenvalues of the exact Hamiltonian, which actually has two kind of interaction. One is a 1 electron operator, electron nuclear attraction and electron kinetic energy, and 2 electron operator 1 by R12 term. And the problem because of which I cannot solve it exactly is the 2 electron repulsion term, the 1 by R12 term. So, if I cannot solve the Hamiltonian, I will define a new kind of an Hamiltonian, which is the Fock operator, where the explicit R12 interaction, the interaction between the 2 electron, I replace them by a physically meaningful interaction, where one is the repulsion of the electron, the Coulomb repulsion, and other is an exchange interaction between the 2 electron, which is a quantum mechanical interaction. So, the exact R12 operator I replace by, which is a 2 electron term, I replace it by 2 effective 1 electron term, and that is why it is called sometime it is a mean field picture. Why it is a mean field picture? And Hartree-Fock theory is often called a mean field theory. That means, so here you see there is an integration over the coordinate of electron 2, and this electron the J, this I have written for a 2 electron system, so that's why the summation is over 2. In principle, I should correct it, I should put it n here, because this is this is a general equation for n electron system, and here I used n by 2. This should have been also made n by 2 here. Now, the reason is that because this is a J is now a dummy variable. So essentially what I am doing, instead of taking the interaction between all the electrons, I am taking an average interaction where each electron is moving in an average field or a mean field of the other electrons. To take a more easier example, so in an ideal world, those who are attending this course, I should interact with all of you one by one. So that's actually an exact interaction. Now suppose I am taking a class where each of you are surrounded by your fellow classmates. So that means, and when I see at you, I see you in the presence of your other classmates. So each of the student I can see in terms of other classmates. So it's a kind of an average interaction. I do not have any knowledge that how do you are interacting with each other explicitly, but I know because we are sitting in the same class, so they are your friends. So I only have an average vector. That's what the Hartree-Fock also give, that each electron is moving in an average field of the other electron. That's why this is called a mean field solution. Second thing to notice is that if I solve this equation f psi I is equal to epsilon I psi I, I will get this eigenvalue equation. If I solve, I will get the solution of the psi I. Now, to define the Fock operator, I need the j and k that also itself contains psi I. So that means I have to, this is a problem. So to get the psi I need to define Fock, and to define the Fock I need to have psi I. So that means this cannot be solved as it is, it needs to be solved in an iterative way. So that I have to first guess a form of the psi, then construct the Fock, diagonalize it, get a new psi, and then again reconstruct Fock. So that's why it needs to be solved in an iterative way. And once we solve in an iterative way, after some time what will happen, the psi I will obtain from the solution of the Fock at 2 successive steps. So one psi I used to reconstruct the Fock and diagonalize it to get a new psi, these 2 psi will be similar. So that means the interaction between the average interaction between the electron has reached to what is called a self-consistent limit. So each electron is moving in an average field of the other electron that reached to a self-consistent picture, and that's why Hartree-Fock is often called an SCF method also, self-consistent field theory. Now, this is a general Hartree-Fock, can be solved like this for atoms, but for molecules this cannot be solved, because you remember the form of the integrals j and k. They are difficult integration, and these integrals are very difficult to calculate for molecules. For atom, because it has a spherical symmetry, these are more easier to calculate. So you can do atomic Hartree-Fock as it is, but for molecule you cannot solve the j and k integrals. So what you need to do, if you cannot solve an equation analytically, one need to resort to numerical method, and one need to solve it numerically by introducing basis sets. So where I expand my psi I as a linear combination of phi I, and at this phi I ranges from 1 to L. The psi i's are molecular orbital and phi i's are atomic orbitals. Now, atomic orbitals means they are the solution of the individual atomic Hamiltonian, and these atomic orbitals are centered on particular atoms. So they are often called an atom centered basis. Now, depending upon what is the nature of the phi mu and how many of them I have considered, that will determine my accuracy. If I take infinite number of them, that will lead me to a complete set. So in that case, my numerical solution is exact, but for all practical applications, I need to somewhat truncate it at it, and that will lead to an basis set approximation. We will discuss more about the structure and the nomenclature of the basis set on the subsequent lectures. But because I am representing my molecular orbitals as a linear combination of atomic orbital, that is why the SCF theory is similar to LCAO-MO theory, linear combination of atomic orbital to generate molecular orbital. And because I am defining the molecular orbital as a linear combination to atomic orbital, it gives me 2 advantages. First of all, for atomic systems, I can solve the Hartree-Fock exactly without resorting to the basis. So I get to the set of known basis functions. So my problem finally remained to find out this combination coefficient. Second thing is that My idea of chemical bonding also comes from the fact that I take the atoms actually undergo linear combination to generate bonding and antibonding orbital. So that chemical intuition still remains in the Hartree-Fock picture. So Hartree-Fock pictures, Hartree-Fock molecular orbitals are very effective for chemical interpretation. So now this was my original Hartree-Fock equation. So I expand the psi I in terms of atomic orbital as a linear combination C nu I phi I and epsilon I C nu I phi I. I left multiply with another set of atom center basis set phi mu star and integrate out. If I get to this integrated form, so this is now I can, so you see the index, I have index of mu f nu and similarly here I have mu nu. So if I write it in a matrix format, this will look like Fc is equal to Sc. So this looks almost like an eigenvalue equation. So this is sometimes it's called a pseudo eigenvalue equation, where my Fock is this term, this integral I have written as Fock, this integral I have written as S, and this S is called an overlap matrix. C is the coefficient and E is my diagonal matrix, contains the eigenvalues at the diagonal. So E is a matrix which contains the epsilons. Few things to notice here. The only term, why I call it a pseudo eigenvalue equation, because of the presence of this S term. Now if this S term was not there, then it would have looked at Fc is equal to Ce, it is an eigenvalue matrix eigenvalue equation. Now what this S actually is, see what this S is. So this is an overlap between atomic orbital mu and atomic orbital nu. Now this mu and nu's are atom centered basis functions. So each of them are centered on different atoms and they are obtained by the solution of the Hamiltonian on that particular atom. We know that the solution of the same Hamiltonian are orthogonal, but if I take solutions of the Hamiltonian which are centered on different atoms and different Hamiltonians, they may or may not be orthogonal. I have no way to a priori guessing it. That is why there can be an overlap between the atomic orbital and this S is called an overlap matrix. So that means to solve the Rithan equation practically, I need to get rid of this overlap matrix. So just going before that, if I want to see how the Fock matrix structure actually looks like, so this is my Fock matrix. I am where Fock is H core plus J and K operators, and if I expand this, this is in the case of the way it's written in the terms of basis, this is how it will look like. I can also expand the J and K in terms of atomic orbitals. So if I do that, what I will left is the AO to MO coefficients and 2 electron atomic orbital integrals. And this H core is of course a matrix consists of the core Hamiltonian terms in the atomic orbital basis. Now, so this term is known, the atomic orbital, 2 electron atomic orbital integrals are known. So my constructing the Fock essentially means the unknown parameter is only the coefficient. So solution of the Hartree-Fock equation actually leads to guessing this coefficient, or I can multiply this coefficient together to get this charge density bond order matrix. So my solution of the Hartree-Fock equation actually becomes guessing this charge density bond order matrix. Now what guess I can make? From the equation, the easiest guess I can make is that my charge density bond order matrix is 0. So that means my Fock matrix is same as my H core, 1 electron part. So when I do start the Hartree-Fock procedure, and we'll see a flow chart how the Hartree-Fock procedure works. So what you can do is that you can actually take this charge density bond order matrix to be 0, and that is famously called as H core guess. So that means I will take the Fock matrix and H core, I will diagonalize it, I will get some set of coefficient. From that coefficient, now I will construct the P, the charge density bond order matrix. So now I will have a 2 electron term. I will diagonalize a new Fock and get a new set of coefficient, reconstruct it, and this is how it will go. And of course, one can take many other kind of guess. In addition to H core, one can get Huckel, one can get Sedlec type of orbitals. So there are many types of guess possible. Now, the main problem what was happening is that my S matrix was not diagonal. So because my original set of 5 mu basis functions are not orthogonal. So what one can do, one can define a new set of basis functions which are actually orthogonal. So that I define a new set of basis function phi mu dash, and if I calculate the overlap between the phi mu dash, they are just diagonal. You see a Kronecker delta here. So what in that new basis, if I switch from phi to phi dash, my Fock matrix now becomes Fc is equal to C. So this is a matrix eigenvalue equation. I can diagonalize it. I can find out the C and the C dash. And I already know the relation between C and C dash. It's C is equal to X into C dash. So I can always go back to the original C and get the original eigenvalue out of this equation. Question is that how I get the X? There are multiple ways of obtaining X. One of the easier option is to take s to the power minus half, what is called a symmetric orthogonalization. Of course, there are other options of choosing the X with different parameters. It has different names. Now, if I want to know the Hartree-Fock algorithm, what I do? First, I give the input data. Remember, to define the Hamiltonian, I need the atomic coordinates, atom numbers, the number of electrons, that means charge and multiplicity. And with that, I will define my Hamiltonian. I will generate the 1 electron integrals, overlap and Coulomb matrices. And from the overlap matrix, I will transform it to the new basis, which will give me the overlap matrix to be now diagonal. I will make a first guess of the density matrix, and easiest guess is to put the density matrix to be 0. I will calculate the Coulomb and exchange integral. So, first time I will put it 0, diagonalize, get a coefficient. With the new coefficient, I will construct Coulomb and exchange integral, construct the Fock matrix, diagonalize the Fock matrix, and I will do this again and again up to the time the convergence is reached. Once the convergence is reached, I will come out of the loop and calculate the energy, forces, dipole moment, whatever I like. And if it has still not converged, I will again go back to the calculation of the Coulomb and exchange term with the new coefficient, or construct a new density matrix out of it, go to the Coulomb and exchange contribution, construct the Fock matrix, diagonalize it again, and see the convergence has reached or not. The convergence will be on two things. First of all, the energy needs to be converged. So, if I do these iterations, after some time the energy needs to be converged. But generally in modern Hartree-Fock programs, the convergence is not only on the energy, but also on the coefficient or the density. So, if the Hartree-Fock has converged properly, the energy and the coefficients both should have converged properly. Now, this is what we define the Hartree-Fock procedure. Remember, this was my Hartree-Fock energy. And if I get to the expression, so the way I will calculate the Hartree-Fock energy, my wave function, that I will use the postulates of quantum mechanics. So, I have an approximate well-behaved wave function. I will put the Hamiltonian in between, and that expectation value will give me energy, or in place of Hamiltonian, if I want to put any other form of the operator, I will get the corresponding property. Now, the orbital energies are defined like this, and one can see that the energy is not twice as the orbital energy. So, if I want to calculate the energy of an H2 molecule, the H2 molecule energy is not same as the twice of the hydrogen molecular orbital energies. It is not the twice electrons of the energy, and in reality you have to subtract this term to j minus k to get to the total energy. Why it happens? In the Hartree-Fock mean field theory, what I am doing? I am having each electron is moving in an average field of the other electrons. So, let us say if I have 3 electrons. So, electron 1 is moving in the average field of 2 and 3. So, that means the the interaction between electron 1 with electron 2 and 3 has been taken. Now, I consider the second electron. The second electron is also moving in the field of electron 1 and electron 3. So, I will take them in an average way. That means, the interaction between the electron 1 and electron 2 is actually counted twice, and that leads to an overcounting. So, to calculate the total energy, if I just addition of the orbital energy is not good enough because it contains overcounting. So, I need to subtract out the overcounting term to get to the total energy of the system. Although the orbital energy actually can lead you to the about the stability of the wave function. So, in principle, all my occupied orbitals should have negative orbital energy to make it stabilize, and my unoccupied orbital should have positive occupied energy. That means, if I put an electron there, this will become higher in energy. So, the determinant, the energy corresponding to the determinant actually increases. Also, other thing is that in the Hartree-Fock picture, only the occupied orbitals are variationally optimized. So, they represent a good set of orbitals. The virtual orbitals are generally garbage of the Hartree-Fock, and they are not variationally optimized. We have seen how to calculate energy. Now, what happens if I want to calculate property, one electron property corresponding to one electron property operator O1? What I will do, I will take the same formula, I will put the O1 in between, take an expectation value, and the one electron property operator actually looks like an H core. So, this will be defined like this. If I expand the psi I equations, this will lead to charge density bond order matrix and an atomic orbital integral. For example, if I want to calculate dipole moment, the classical definition of the dipole moment is a vector, just check the arrow sign, and with a charge times some kind of a displacement. So, the corresponding expression for the quantum mechanical calculation will be like this. So, I have to take an expectation value, and of course, there is a classical nuclear contribution to the dipole moment, and I can define the dipole moment matrix. So, with every Hartree-Fock calculation, we will see the dipole moment, and this actually have very little additional cost over the Hartree-Fock calculation, energy calculation. So, for every Hartree-Fock calculation, you will see the dipole moment values are printed below. Other important thing is the population analysis. Remember, we talked of charge density. So, this charge density is nothing but psi star psi, and if I that is what the density is. Probability density was integration of the psi star psi, and of course, you can replace by the integration by a summation. So, if I expand this size, the molecular orbital in an atomic orbital, what I will get is that I can write it like this. I can put the coefficient here. So, overall I can define a charge density bond order matrix. So, I have two terms. The first one, these two C's are actually called P, which is a charge density bond order matrix, and this size are actually an overlap matrix. So, this is how it can be defined, and we know that the total number of electron can be calculated by integrating the charge density bond order, the charge density over the whole space dr. So, which will essentially lead to the trace of this PS matrix element. Now, this is the total number of electron. What I can do is that I can now calculate the net charge associated with an atom. How I can do that? I can take the same expression and I can integrate. So, this mu are atomic orbital basis function, and these atomic orbitals are centered on a particular atom. So, that means I can take a sum of the atomic orbital which are localized on a particular atom A. So, that will give me the electronic contribution of the charge, and of course, there is a nuclear charge which is positive. So, if I subtract this electronic contribution from the nuclear charge, this will give to the net charge associated with an atom, and that is what is called a Mulliken population analysis. So, this gives me how much charge is associated on a particular atom. Of course, a atom which is more electronegative, they will have more negative charge, which is less electronegative, will have less negative charge, maybe a positive charge. But the problem is that this PS, I can write it like this. So, the stress is invariant to the permutation between those two matrices. So, that means I could have written the Sn as S alpha V S minus 1 alpha, and this will also give the same value of n. So, that means the way I am writing the n is unique in terms of P and S. So, I can also write an alternative definition of the population analysis, whereas QA is ZA minus S to the power half P S to the power half, where I taken the alpha to be half. This is also a valid definition of n, and if I sum it over, the net charge will be 0, and if I just sum this charge, this will give me the value of the n, and this is called a Lautin population analysis. Now, you may ask which population analysis I should use. There is no straightforward answer, because none of the population analysis is unique, and it is very difficult to say one is better than the other. You can have other population analysis, you can have Hurst-Field population analysis, you can have natural population analysis. There are multiple ways of doing this population analysis. They are very good for chemical interpretation, but remember, they are not unique. So, I hope by now you have understood what Hartree-Fock is. It is the method where you choose a single determinant form of the wave function, and by variational optimization, you get the best possible single determinant, and you have seen how to solve it in terms of basis function, how you can express those Hartree-Fock molecular orbital as a linear combination of atomic orbital, how you can calculate energy, and the total energy is not sum of the orbital energy, how you can calculate properties and population analysis. So, now what we will do, we will run an ORCA calculation and see what are the various terms what you have discussed, what they mean in terms of a actual practical computational chemistry calculation, and we will analyze the output file. Thank you.